Welcome. Today we're diving into the fascinating world of large language models, or LLMs. These powerful AI systems have revolutionized how machines understand and generate human language. But what's the secret sauce behind their impressive abilities? It's something called the attention mechanism. In this video, we'll break down what attention is, why it matters, and how it helps LLMs make sense of complex text. Whether you're new to AI or just curious about how these models work, you're in the right place. Let's start by understanding what LLMs are and why attention is so important in their architecture. Large language models, or LLMs, are advanced artificial intelligence systems designed to process and generate human-like language. They're trained on massive amounts of text data, learning patterns, grammar, and even context. LLMs can answer questions, write essays, translate languages, and much more. But to do all this, they need to understand not just individual words, but the relationships between them. That's where the attention mechanism comes in. Before we get into attention, let's quickly look at how LLMs process language at a high level. When an LLM receives a sentence, it doesn't just read it from start to finish like a human. Instead, it breaks the sentence into smaller pieces, often called tokens. Each token could be a word, a part of a word, or even a punctuation mark. The model then tries to understand how these tokens relate to each other. This process is complex, especially for long sentences or paragraphs. That's why traditional models sometimes struggle with context. Attention mechanisms help solve this problem by allowing the model to focus on the most relevant parts of the input. One of the biggest challenges in language processing is understanding context. Words can have different meanings depending on where they appear in a sentence. For example, the word bank could mean a financial institution or the side of a river. Traditional models often miss these nuances because they treat each word independently. The attention mechanism changes this by helping the model weigh the importance of each word in relation to others, capturing context more effectively. But what exactly is the attention mechanism? In simple terms, attention allows the model to look at all parts of the input sentence and decide which words are most important for understanding the meaning. Instead of treating every word equally, the model assigns different weights to different words. This way, it can focus more on the words that matter most for the task at hand, like answering a question or translating a sentence. Let's break down how attention actually works inside an LLM. When the model processes a sentence, it calculates a score for each word, showing how much attention should be paid to it. These scores are based on the relationships between words. For example, in the sentence, "the cat sat on the mat," the model might pay more attention to cat and mat when figuring out what sat refers to. This dynamic weighting helps the model understand meaning more accurately. Key type of attention used in LLMs is called self-attention. This means the model looks at every word in the sentence and considers how it relates to every other word, including itself. Self-attention allows the model to capture complex dependencies, like when a word at the beginning of a sentence affects the meaning of a word at the end. This is especially important for understanding long sentences or paragraphs. Self-attention is powerful because it lets the model build a rich understanding of the entire input, not just parts of it. By comparing every word to every other word, the model can pick up on subtle cues and relationships that would otherwise be missed. This leads to more accurate language understanding and generation, making LLMs much better at tasks like translation, summarization, and question answering. Attention scores are the numbers the model uses to decide how much focus to give each word. These scores are calculated using mathematical formulas that compare the similarity between words. The higher the score, the more attention the model pays to that word. This process happens for every word in the sentence, creating a map of relationships that guides the model's understanding. Calculate attention scores. LLMs use three main components: queries, keys, and values. Each word in the sentence is turned into a query, a key, and a value. The model compares queries and keys to find out which words are related, then uses the values to build the final output. This system is inspired by how we search for information in a database, matching questions to answers. The process of calculating attention involves multiplying the query and key for each word, then applying a softmax function to turn the results into probabilities. These probabilities become the attention scores, which tell the model how much to focus on each word. The values are then combined using these scores, producing a new representation of the sentence that highlights the most important information. LLMs don't just use one set of attention scores, they use many in a process called multi-head attention. Each head looks at the sentence from a different perspective, focusing on different relationships between words. The results from all the heads are then combined, giving the model a richer and more nuanced understanding of the text. This is a key reason why LLMs are so effective at handling complex language tasks. Multi-head attention allows the model to capture different types of relationships in the text at the same time. For example, one head might focus on grammar while another looks at meaning or context. By combining these different views, the model can understand language more deeply and make better predictions. This flexibility is what sets LLMs apart from earlier models. Attention mechanism is a core part of the transformer architecture, which is the foundation for most modern LLMs. Transformers use layers of attention to process text, allowing them to handle long sentences and complex structures. This architecture has led to major breakthroughs in natural language processing, powering models like GPT and BERT. Transformers stack multiple layers of attention on top of each other. Each layer refines the model's understanding of the text, building up from simple relationships to more complex ones. As the input passes through these layers, the model becomes better at capturing meaning, context, and subtle nuances in language. In a transformer, there are two main parts, the encoder and the decoder. The encoder reads the input text and builds a representation using attention. The decoder then uses this representation to generate output, like translating a sentence or answering a question. Attention is used in both parts to ensure the model focuses on the right information at each step. Encoder uses self-attention to analyze the input text. By comparing every word to every other word, it builds a detailed map of relationships. This helps the model understand the full meaning of the input, including context, grammar, and intent. The output of the encoder is a set of vectors that represent the input in a way the model can use for further processing. Decoder also uses attention, but in a slightly different way. It looks at both the output it has generated so far and the encoder's representation of the input. This allows the model to generate output that is accurate and relevant, whether it's translating a sentence or answering a question. Attention ensures that the decoder always has access to the most important information. Since attention treats all words equally, regardless of their position, transformers use something called positional encoding. This adds information about the order of words in the sentence, helping the model understand sequences and structure. Without positional encoding, the model wouldn't know if a word came first or last, which is crucial for meaning. The order of words can completely change the meaning of a sentence. For example, the dog chased the cat is very different from the cat chased the dog. Positional encoding helps the model keep track of word order, ensuring that it understands the correct meaning and context. This is a key part of how LLMs achieve human-like language understanding. Researchers often visualize attention scores to see which words the model is focusing on. These visualizations show lines connecting related words, revealing how the model interprets relationships in the text. By studying these patterns, we can better understand how LLMs make decisions and where they might make mistakes. Attention maps are powerful tools for interpreting model behavior. They can highlight which parts of the input are most influential for a given output. For example, when answering a question, the model might focus on specific keywords in the passage. By analyzing attention maps, researchers can diagnose errors and improve model performance. While attention is powerful, it's not perfect. Sometimes the model might focus on the wrong words or miss important relationships. Attention scores can also be hard to interpret, especially in very large models with many layers. Researchers are constantly working to improve attention mechanisms and make them more transparent. As LLMs get larger, attention mechanisms need to scale as well. Handling longer texts and more complex relationships requires more computational power and smarter algorithms. Researchers are developing new techniques to make attention more efficient, allowing models to process bigger inputs without losing accuracy. One way to make attention more efficient is through sparse attention. Instead of looking at every word in the input, the model focuses only on the most relevant ones. This reduces the amount of computation needed and speeds up processing. Sparse attention is especially useful for very long documents or conversations. Attention mechanisms are used in a wide range of applications, from chatbots and virtual assistants to translation and summarization tools. By helping models focus on the most important information, attention improves accuracy and makes AI more useful in everyday tasks. It's a key reason why LLMs are so versatile and powerful. Machine translation, attention helps the model align words and phrases between languages. For example, when translating a sentence from English to French, the model uses attention to match each English word to its French counterpart. This leads to more accurate and natural translations, even for complex sentences. When summarizing long documents, attention helps the model pick out the most important points. By focusing on key sentences and phrases, the model can generate concise and informative summaries. This is especially useful for news articles, research papers, and other lengthy texts. In question-answering tasks, attention helps the model find the relevant information in a passage. When given a question and a block of text, the model uses attention to highlight the parts of the text that contain the answer. This leads to more accurate and reliable responses, making LLMs valuable tools for research and learning. Chatbots use attention to keep track of conversation context and respond appropriately. By focusing on the most recent and relevant parts of the dialogue, the model can generate coherent and context-aware replies. This makes interactions with AI assistants feel more natural and human-like. In generating text, attention helps the model stay on topic and maintain coherence. By focusing on relevant parts of the input and previous output, the model can produce longer and more meaningful passages. This is crucial for tasks like story writing, code generation, and creative content creation. Search engines use attention mechanisms to match user queries with the most relevant documents. By analyzing the relationships between words in the query and the documents, the model can rank results more effectively. This leads to better search experiences and more accurate answers to user questions. Recommendation systems use attention to personalize suggestions for users. By focusing on the most relevant user preferences and behaviors, the model can recommend products, movies, or articles that are more likely to interest the user. Attention makes these systems smarter and more responsive to individual needs. In speech recognition, attention helps the model align spoken words with written text. By focusing on the most important parts of the audio signal, the model can transcribe speech more accurately. This technology powers virtual assistants, transcription services, and voice-controlled devices. Attention isn't just for text, it's also used in image captioning. Here, the model looks at different parts of an image and focuses on the most relevant features when generating a description. This allows AI to create accurate and detailed captions for photos and videos. Multimodal models combine text, images, and sometimes audio. Attention helps these models align information from different sources, like matching a caption to an image or syncing subtitles with video. This makes AI more versatile and capable of handling complex, real-world tasks. The idea of attention in AI is inspired by how humans focus on certain things while ignoring others. Just as we pay more attention to important words in a conversation, LLMs use attention to prioritize information. This human-like approach helps models understand language in a more natural and effective way. Researchers are always looking for ways to improve attention mechanisms. New techniques like adaptive attention and memory-augmented attention are being developed to make models even smarter. These advances help LLMs handle more complex tasks and understand language with greater depth. One of the benefits of attention is that it makes models more explainable. By showing which words or features the model focused on, we can better understand its decisions. This transparency is important for building trust in AI and ensuring that models behave as expected. As AI continues to evolve, attention mechanisms will play an even bigger role. Future models will use more advanced forms of attention to handle increasingly complex language and multimodal tasks. This will open up new possibilities for AI in fields like education, healthcare, and entertainment. Let's recap what we've learned. Attention mechanisms help LLMs focus on the most important parts of the input, capturing context and relationships between words. Self-attention, multi-head attention, and positional encoding are all crucial components. These techniques make LLMs powerful tools for understanding and generating language. Attention mechanisms have transformed the field of natural language processing. They enable models to handle complex tasks, generate human-like text, and adapt to a wide range of applications. As research continues, we can expect even more impressive advances in AI language understanding. The future of attention mechanisms is bright. With ongoing research and development, we'll see even smarter and more capable language models. These advances will make AI more useful, trustworthy, and accessible to everyone. Stay tuned for exciting developments in this rapidly evolving field. Attention mechanisms are at the heart of how LLMs work. By allowing models to focus on what matters most, they enable a new era of intelligent language processing. Whether you're a researcher, developer, or just curious about AI, understanding attention is key to appreciating the power of modern language models. Thank you for joining us on this journey into the world of attention mechanisms and LLMs. We hope you now have a clearer understanding of how these models work and why attention is so important. Stay curious and keep exploring the amazing possibilities of artificial intelligence.